Hello. In this lecture, we are going to talk about hypothesis testing in simple linear regression model. Particularly, we are going to talk about unbiasedness and consistency property of OLS estimators, which we have already derived during the class, and we're going to make a brief review of those derivations. Second point is hypothesis testing and confidence intervals in simple linear regression model using R programming language. A third point that we are going to discuss is the problem of heteroscedasticity, and we're going to give several examples of heteroscedasticity and show those examples in R. And finally, we're going to talk about Gauss-Markov theorems. Okay. So to work with this lecture, to perform computations of this lecture, you have to download two libraries. One is AER, Applied Econometrics with R, and Math library, and also Scale library. Scale library is providing you with generic plot scaling methods in plot function. Okay, let's start with our generic simple linear regression model given by yi equals to beta 0 plus beta 1 xi plus epsilon I. Yi is the dependent variable, xi is the independent variable. So we want to explain yi, the dependent variable or the regressant, using xi, the independent variable, or sometimes referred to as a regressor. Okay, and obviously we have error term here, which accounts for all the differences between this line. This is obviously a function of a perfect line, so all the difference between the observed data and the perfect line is accounted for under the error term, epsilon I. Okay, and beta 0 and beta 1, they are parameters, they're population parameters, and we need to estimate those parameters consistently using the data at hand. Okay. So how we derive the OLS estimators? Obviously, we are minimizing the sum of squared residuals, and as a result of this minimization problem, we get a very well-defined formula for beta 1 and beta 0. So those guys, they have hats standing for the fact that we have computed those values using the sample data instead of the population data. Okay. By the way, X bar here stands for the sample mean of X's, and Y bar stands for the sample mean of Y's. Okay. So we have two well-defined formulas for OLS estimators, right? And they are going to be unique given the regularity conditions. If you remember, we talked about the uniqueness of OLS estimators. So as a result of the minimization problem, we got two equations, two linear equations in two unknowns, and under these conditions, obviously, those two equations, they are just identified, and therefore the parameters, the unknowns, beta 1 and beta 0 hats, they are uniquely identified. Okay, so we have several assumptions about the OLS estimators. First, actually about the population regression. So the first assumption is that the conditional expectation of errors given xi's, given the regressors, is equal to 0. So basically, you can fix x at any point that you want, and if you find the average of errors in the population regression line, then you are going to receive 0. That is the essence. We have shown several examples of that. If you remember, during the class, we drew the regression line and we explained this assumption. This assumption is sometimes referred to as strict exogeneity assumption. Exogeneity assumption. Okay. The second assumption tells us that the data comes from simple random sampling. So saying that YIXI or IID stands for the fact that we are making simple random sampling from the population. Okay. And third assumption is about finite kurtosis. So we say that large outliers are unlikely. Actually, these two assumptions are helpful to make sure that CLT can be applied. So given these three assumptions, then central limit theorem can be applied. So in large samples, OLS estimators are going to be normally distributed, approximately normally distributed, and as n goes to infinity, this convergence and distribution gets more and more precise, right? Okay, now we have to prove that under these assumptions, not only we have normally distributed OLS estimators, but also we have unbiased and consistent OLS estimators. Let's start with the first parameter, beta 1 hat. First estimator, beta 1 hat. So this is not a parameter actually, because parameter is basically denoted by beta 1 itself without any hat, right? When we put hat, it means the animal is estimated using the sample data, is calculated using the sample data. So this is the formula. This guy within the brackets, you see, up to this point, within the red parentheses, is nothing but a formula for beta 1. Obviously, we use an alternative formula for beta 1 hat. It was covariance of xi yi divided by variance of xi, right? So you can have a look at this. The denominator part, this is actually the formula for variance multiplied by n. So basically you can multiply both guys by n, both denominator and numerator by n, nothing is going to change. So basically the denominator of this blue circled expression is basically variance of xi multiplied by the number of observations. And the same stands for the numerator. The animal given in green circle, that is nothing but the covariance of x and y, covariance between x and y multiplied by the number of observations. And here we're conditioning on x. Okay, you have to condition on x. So for any value of x, you fix the values of x and then compute the OLS estimators, and we are assuming that in that case the expectation of beta 1 hat is going to be equal to the true parameter value. Okay, so the rest is very straightforward algebraic manipulation. Look at the second part here. What is this? This is, so basically instead of yi minus y bar, we just plug the population definition of, so instead of y bar, we just plug the population definition of yi, because in the previous slide, you can see that in the previous slide we said that yi is nothing but beta 0 plus beta 1 xi plus epsilon I. So we basically plug that expression for yi, and then we get something like this. And in the third line, what we do is, you see, instead of y bar, we are plugging, you see, we're plugging the formula we're plugging this formula. So y bar from this formula is equal to beta 0 plus beta 1 times x bar, right? So we basically plug for y bar, and as a result we receive, you see, beta zeros are going to cancel each other out. So let me rewrite it here. Beta 0 plus beta 1 x bar, right? So this is for y bar. Instead of y bar, we write the its definition. In that case, beta zeros are going to cancel each other out, and we're going to be left with beta 1 xi term minus beta 1 x bar, right? So, and epsilons is not cancelled out, so they stay in the equation. It's quite straightforward. Then we do further manipulation. So basically we see that we have common terms. You know, the first two guys here, this guy and this guy, they share a common term beta 1. So we take beta 1, we simplify it, saying that I can rewrite it as beta 1 times so xi minus x bar is going to be a common term for the first two elements. So we can say that the equation can be written as beta 1 xi minus x bar squared, and obviously we are summing over i's, right? And then you have plus xi minus x bar times epsilon I, right? And obviously we have to divide by xi minus x bar. So that is what this expression is about. You see, so we simplified. We know that beta 1 is constant parameter, right? So therefore we can take it out of the expectation operator. So beta 1 times expectation of xi minus x bar squared divided by xi minus x bar squared by conditioning on xi values plus, you see, the expectation is a linear operator, meaning that, so if you have expectation of x plus y, you can basically split it in two parts. You can say that this is equal to expectation of x plus expectation of y. So because of this fact, we can split the expectation, you know, this whole thing can be split in two parts, okay? So because expectation is a linear operator. Anyway, and finally what happens, we see that in the first term, you see, xi minus x bar squares, they cancel each other out, so we receive 1 here, so beta 1 is left alone, plus another term, xi minus x bar divided by xi minus x bar squared, this term, times the expectation of epsilons given xi's. Remember, here we fixed xi's, so we treat xi's as a deterministic variable because we assume that we fix their values. So therefore, you know, we treat it as a constant, and therefore we use the relationship that, you know, if you have expectation of alpha times y, for example, you can write it as alpha times expectation of y, given that alpha is a fixed constant. So we treat x's as fixed constant. The whole term here, red within the red rectangle, is treated as a fixed term, and therefore we can basically put it out of the expectation sign, and what we receive in the end, this term is multiplied by expectation of epsilon I given xi's, right? But based on this assumption 1, we suppose that expectation of epsilons given xi's is equal to 0, so the whole term cancels each other out, and what we receive is, we receive that expectation of beta 1 hat, you know, the estimator given xi values is actually equal to the true value of beta 1. Okay, and that is the definition of the unbiasedness assumption. And one more thing, probably we need assumption 2 here to make sure that, you see, this term here within the red rectangle is not infinity, right? So therefore we suppose that we have finite kurtosis, so you have finite variance. Whenever you have finite kurtosis, remember that, it implies that you will have finite variance. Finite kurtosis implies finite variance, basically. Okay, that is how we receive the we receive the unbiasedness of beta 1 estimator. Okay, and the third assumption here is, the second assumption actually, idea assumption is important because you cannot get this guy here if you don't do simple random sampling. It's not impossible. It's not possible actually. So we need all those three assumptions actually for unbiasedness of OLS estimators. The same goes for beta 0 hat, the intercept estimator. So we know that the formula for beta hat 0 is y bar minus beta 1 hat times x bar. So we basically plug for this formula, and then we fix xi's. You see, we basically say that if you fix xi values to a continuum of xi's, then and if you do continuous, if you systematically sample by fixing xi's, if you systematically sample on yi's by fixing xi's, you will, on average, your estimator is going to be equal to the true parameter value. Anyway, so in the second line, what we do is, we just repeat the same thing. Actually, what we do is, instead of y bar, we basically plug the definition. So instead of y bar, we plug actually instead of beta 1 hat, we plug the true value of beta 1, because we have already shown that beta 1 hat is an unbiased estimator of beta 1. So therefore we can interchange beta 1 hat and beta 1. So later on we're going to plug. So basically, if you take the average of both sides, you will get y bar is equal to beta 0 plus beta 1 times x bar plus epsilon I bar, right? We know that the average of errors is going to be 0. Okay, this guy falls from the equation in the end. And we basically plugged for y bar. You see, this guy itself is nothing but y bar itself. This guy falls, and we receive what? We receive expectation of beta 0 plus beta 1 x bar minus beta 1 x bar, and all these guys cancel each other out, right? Yeah. So these two guys cancel each other out, and I think we forgot one term. Just a second. So if you rewrite it, you will receive what? You will receive beta 0 plus, because expectation of a constant is constant, so beta 0 plus beta 1, expectation of beta 1 x bar minus beta 1 x bar, which is 0, and you get plus expectation of epsilon I given xi, which is also 0 by assumption 1. Therefore, you receive expectation of beta hat 0 equal to the true value of beta 0. So basically, both beta hat 1 and beta 0 hat, both of them are unbiased estimators. Okay, they are converging. Basically, their expectation is equal to the true value of the parameter. Okay, and obviously, unbiasedness property implies consistency, but not vice versa. So once you have this unbiasedness property, you can say that these estimators are also consistent. Okay. Now let's have a look at the hypothesis testing confidence interval estimation in simple linear regression model using R. Now let's think of the generic example. You have test scores average test score in school I defined by student to teacher ratio at school I, right? This is the supposed, we suppose that this is the true relationship, okay? And the problem here is that we cannot, even if the model is correct, we cannot get these parameters correctly, true values of these parameters, because we are operating in the sample level. We are dealing with the sample data. We don't have the population data. Okay, it may happen that you estimate these parameters, for example, beta 1 in our previous estimations was equal to, beta 1 hat actually, was equal to minus 2.27, but because we are operating in the sample level, it may happen that the true value of beta 1 is equal to 0, although we get minus 2.27 in the sample, right? So therefore, we need a formal test. We need a hypothesis testing to test whether this, parameter, the true parameter value, can be equal to 0 in population, okay? Right? So if beta 1 is equal to 0 in population, it would imply that student to teacher ratio variable is completely useless as a policy variable. Okay, so you cannot advise the ministry to decrease the class sizes to boost the student performances. Therefore, we need hypothesis testing about those parameters. Again, we are operating in the sample level. We don't have access to the whole population data, right? Now, let's perform this hypothesis testing in R. This is very simple. First, we have to attach this library, AER, Applied Econometrics, with R, because the dataset, Canadian Schools dataset, lies within that library. And then we call the library, we call the dataset. We attach the dataset using data function, and we define these two new variables, score and SDR variables, and put that within that data frame, Canadian Schools data frame, and then we make this, we basically run the linear regression model of score to student to teacher ratio, okay, and then we summarize it. Now let's see what we get as a result. This is the output of the summary function in R, okay. So we got coefficient estimates for intercept 698, SDR, like the coefficient estimate for beta 1 is equal to minus 2.27. So the value of beta 0 hat is equal to 698. That is the intercept. And beta 1 hat is equal to minus 2.28. Okay, these are estimates, sample values. But it may happen that the population value is equal to 0. That is what we want to test. And this summary function is actually, this built-in summary function is actually reports the results of this hypothesis testing, that beta 1, the true value of the parameter, is equal to 0 in population, and alternative hypothesis is that beta 1 is not equal to 0. Now let's pay attention to this guy here, to the green circled row. So this is the beta 1 estimate, the coefficient of SDR variable. We got minus 2.28, and you can see that t-value is greater than 2 in absolute value, so we have to reject the null hypothesis. So this is false and this is true. And also you can use, alternatively, you can use p-value. You see, you got 3 stars here. 3 stars means that this, SDR variable is statistically significant. I mean, the coefficient of SDR variable beta 1 is statistically significant, meaning that its population value cannot be equal to 0 with high probability, okay? So that is the meaning of 3 stars. Here you can see that 3 stars stands for the fact that even at 0.1 level of significance, you reject this hypothesis. 2 stands for the fact that at 1% level of significance, you reject this hypothesis, null hypothesis, and 1 stands for 5%, dot stands for 10%, okay? And nothing, no star, no stars and dots will be there if the p-value is greater than 10%. Okay, and also we got residual standard error, that is the standard error of regression, denoted by SER, that is equal to 18.58, and the R square is equal to 5%. So this is really a bad fit. It means that only 5% of variation in dependent variable is explained by the model, by the independent variable. Okay, so that is quite poor fit, just 5%. Right, and then what else? Yeah, the same hypothesis testing is conducted for the intercept parameter. You see, the intercept parameter estimates is equal to 698 in the sample, but the first line here is actually reporting the coefficient estimate, also reports the result of the null hypothesis that beta 0, the true value of beta 0 in population is equal to 0, and the alternative is that beta 0 is not equal to 0. And you can see that that null hypothesis is also rejected at even 0.1% of significance level. Okay, so that is really useful function. This summary function is really useful. Remember, after you run the linear model, if you just print that, you will only get the coefficient estimates, but once you summarize it, you get these results of hypothesis testing. So up to this point, we understood why hypothesis testing is important in the framework of linear regression model, because it may happen that you receive some coefficient different from 0, but the real value of that is equal to 0, which means that a particular variable is not important, a particular regressor is not important for explanation of the dependent variable. Okay, therefore we need to test the hypothesis. Remember that. Now let's move to the confidence interval. So there is confidence function in R which is dealing with that, but you know the default value, default confidence level is equal to 95%. So if you want to change it, you have to pass the so-called level parameter. Let's have a look. Have a look at that. So confident linear model, you can see that it gives you the default 95% confidence interval. You see, so the true intercept value will be covered by this interval, by this lower and upper bound, the 95% probability. The same goes for STR. The beta 1 parameter, true value of beta 1 parameter, is going to be covered by this interval with 95% probability. Now what we want to do is we want to change the confidence level to 99%. So for that you have to supply the additional level parameter equal to 99%. Okay. So but here we have a problem. You know, this summary function and confidence function, they are a little bit problematic because both of them are operating on the assumption that you have homoscedastic errors. So we're assuming that, you know, summary function and confidence functions, they are presupposing that you have homoscedastic errors. The variance of errors are not changing across observations, across x's. But in reality, it may not be the case. Okay, in reality, most of the data is heteroscedastic. So whenever you have heteroscedasticity problem, confident and summary model outputs, you know, related to the confidence interval and hypothesis testing, they become invalid. They may become invalid. Okay, and one more thing that I want to point out is, remember that heteroscedasticity problem does not have any effect on unbiasedness or consistency of OLS estimators. They still remain unbiased and consistent given the three assumptions we mentioned here. Given these three assumptions, you will always get consistent and unbiased estimators, OLS estimators. But if you have heteroscedasticity problem, then the standard errors are going to be problematic, and that is going to affect the hypothesis testing problem and also the confidence intervals. Those guys are going to be biased, problematic. Remember that. Because hypothesis testing is closely linked to the standard errors, right? Look at this, for example. Here, to get a t-value, what you are doing, you are basically taking the coefficient estimate and dividing it by 9.4. Like if you divide 698 by 9.46, you are going to receive 73 approximately. The same goes for the second. To get a t-value, you have to divide the parameter estimate, which is minus 2.27, by 0.47. So you see, the denominator includes the standard error of the parameter, and if your standard errors are false, it means that your confidence, your hypothesis testing is going to be problematic because you are using wrong standard errors. So therefore, heteroscedasticity problem, changing variance of errors is problem only for hypothesis testing and confidence intervals, because only those guys are related with the standard errors. Consistency and unbiasedness, they are not using standard errors, and therefore OLS estimators, they still remain consistent, unbiased, given those three assumptions. Remember that. Now let's give some examples of heteroscedasticity problem when the error variance is changing, although the average of errors, the strict exogeneity assumption holds, but you have the heteroscedasticity problem, meaning that the magnitude of errors are changing, although they are average, the conditional average is equal to 0. We're going to talk about, we're going to give three examples. One example is the case when we use dummy class variable for big and small class sizes. Then we create a fictitious problem, heteroscedastic data. Okay, and the last example is going to use another real data set where we want to explain wages using the years of education, years of schooling. Now let's move to the first example. So suppose we are creating a new variable t, dummy variable. You see, this dummy variable is taking the value of 1 if str variable is less than 20. So if you have a small class size, then this t variable receives the value of 1. 0 if str variable is greater than or equal to 20. So we have some threshold. We say that if the class size, if the student to teacher ratio is greater than or equal to 20, then we'll suppose that this class size is large, otherwise the class size is small. Okay, now let's compute the averages for each, compute average scores when class size is small and when class sizes are large. You see that the mean score for small class sizes is equal to, it's not given here, so we just save it and under this mean score for D1 and mean score D0 respectively, and then we're going to plot it. This plotting, the scatter plot is very simple, right? So you basically show the variable that you want to put on the y-axis and then tilde sign the variable that you want to put on the x-axis. PCH19 is standing for the field circles. You want the circles, the scatter plot to use field circles, and then here you basically set size of these symbols, those circles. Here you adjust the color to steel blue, and then this is the labels. These are the labels, and then you put the general title of the plot. And if you want to add points, you basically use points function. I guess it is from Scales library. You see, you basically put the average for large class sizes at this y value, and where x is 0, where d variable gets the value of 0, because we said that for large class sizes d variable gets the value of 0. The same goes for small class sizes. Now let's move on. We receive this kind of scatter plot. You see that the mean score for large class sizes is smaller than the mean score for small class sizes, and on average, you can see that the errors, the deviation from this average, this red point, you see the deviation. If you count the deviations of these points, the vertical deviations of these points from the red dot, you can see that on average it is 0. This is how this is what you can see. You see, on average, the errors, the deviations from the red point is equal to 0 in both cases. But the problem is that the magnitude of errors, you see, the magnitude of errors are much larger in this case, in the small class sizes case. You see, the magnitude is very large, but here the magnitude is quite small. This is the problem of heteroscedasticity, when the errors, the variance, the magnitude of errors are changing by the value of x. That is the definition of heteroscedasticity problem. You see, although the average of errors, again, average of errors is 0 when you fix it at 0 or at 1, when you fix the d variable, class size variable to 0, you will see that on average errors, the deviations from red point is 0. The same for the small class sizes, but the magnitude is changing. Okay. So again, the problem with the summary and confine functions in R is that they do not take the heteroscedasticity problem into account. Okay, so we have to get around this problem. And one more thing, I want to give you the interpretation of coefficients in simple linear regression model when you have binary regressor. You see, if this is our model, you see beta 0 plus beta 1 times ti plus epsilon I. So if you take the expectation of yi by fixing di to 0, what you receive is just set d to 0 in this regression. Let me use red color. You see, just set d to 0 here. If you set it to 0, you will receive beta 0, and that's all. Because like expectation of errors, you know that expectation of epsilon I is given gi equal to 0 is going to be equal to 0 by the strict exogeneity assumption. Therefore, we just deleted. Just a second, I just deleted. So basically, the OLS estimate for intercept stands for the average of scores in large class sizes. And now let's set d variable, the class size variable, to 1, so to small class sizes. What we see is, if you do that, you see, if you set di variable to 1 here, your regression is going to be equal to this expectation. Take expectation of both sides. You know that expectation of parameters constants is basically equal to constant. So beta 0, expectation of beta 0 is still beta 0. Expectation of beta 1 times 1 is beta 1, and expectation of epsilons are equal to 0, right, by the strict exogeneity assumption. So you get this kind of thing for conditional expectation of y's. So what does it mean? It means that beta 0 is going to give you, is going to be equal, the estimate of beta 0 is going to be equal to average scores in large class sizes. Whereas beta 1, the beta 1 estimate, the estimate of beta 1 in the linear regression is going to be equal to the average scores in the difference of average scores in small class sizes and large class sizes. That is all. Okay, we can have a look at that. You see, if you run linear regression of scores on the dummy variable, this binary variable of small and large class sizes, what you get intercept value equal to 650, and you get the beta 1 value, beta 1 hat value equal to 7.1. So that is the average difference between small and large class, average difference in scores between students studying in large versus small class sizes, right? Okay, we can receive these values alternatively using the conditional mean of scores by fixing the class size to large and small. You see, in large class sizes, the average score is going to be equal to 650. In small class sizes, the average score is going to be equal to 657, and beta 1 hat is actually the difference between the two guys, okay, which is approximately equal to 7, right? You can see that the parameter estimate for beta 1 is equal to 7.1. Now let's move to the next example where we have some fixtures problem. We are creating errors. You see, errors are created in such a way that all of them are normal. So we have 100 observations in our data set. The first 25 are created from normal distribution with standard deviation of 10, but the mean is equal to 0, so it is not, the default value of the mean is equal to 0, therefore it is not given there. We don't pass that mean parameter. The next 25 values of errors, they're also normal, but normal with mean 0 but standard deviation 15, and so on and so forth. So by x values, so each value, the error variance is basically increasing by values of x. You can see that the first 25 values of x is going to be equal to 10. The next 25 value of x is going to be equal to 15, and so on and so forth. So as you increase x's, you are going to receive larger and larger deviation in errors. Now here we are using the plot function. Obviously we define the the fixtures y, fixtures dependent variable, which is found by this equation, and then we basically plot it. We estimate the regression function and then plot everything, add the regression line using the AB line function, and then what we want to do is we want to add the box plot, you see, at each x value. We know that the first 25 values of x's are going to be 10, the next 25 values is going to be 15, the next 25 is going to be 20 and 25, right? So we want to add box plot to the graph at each point. So the first we'll take the first 25 observations, okay, and plot the box plot for errors. And add is true, meaning that we are adding the box plot to the existing plot. Remember that, okay? And this is color and border colors, okay? And we receive this kind of interesting plot. You can see that where x values are equal to 10, you see we got small variation. You see the range is very small, and also the interquartile range is very small. And as you increase the x values, as you move to 25, you get larger and larger range, which means that you will get higher standard deviation, higher variance of errors as you increase x's. But pay attention to the fact that on average the errors are 0. Like if you fix it at 10, the average of errors is basically 0. They are kind of cutting this regression line, because remember that this line here in the box plot, that is median, that is not the mean. But on average, you can see, like by visual examination, inspection, you can see that the average, on average, the errors, the deviations from the line, is 0, right? So that is the heteroscedasticity problem. Yet, another example is about wages and years of schooling. This is a real data set taken from current population survey data. And it also comes from AER package, remember that. Okay? So it's likely, let's talk about our expectations. It's likely that higher educated people earn more than lower educated people, right? That is our expectation, a priori expectation. And also, think of this problem. If you are if you have higher number of schooling years, if you have better education, it is obviously possible for you to get well-paying jobs. Also, for some reason, you may accept a job which is not paying that well, right? But if your education level is low, first you have to, it is less likely that you will be able to get a well-paying job. That is in the first place, okay? So the low-skilled workers, okay, they're more likely to, high-skilled workers, highly educated people, they are more likely to meet the requirements for the well-paid jobs than workers with less education, for whom opportunities in the labor market are much more limited. Therefore, what we expect is this. First, we're expecting that highly educated people, they're going to earn more on average compared to the, poor educated people, and also the variance of errors, the variance of earnings, let's say, for highly educated people is going to be more, because some highly educated people, they may take up poor paying jobs too. Therefore, you will get very high variance in the earnings of highly educated people compared to the variance of earnings of poor educated people. Now let's see whether these expectations are justified. Okay, we're going to use, again, attach the library, attach the data, and then summarize the data. You see, what we see is the mean earnings is 16, the mean years of schooling is 13, and so on and so forth. Now let's plot it. First, we are running the regression of earnings on education, plotting the education versus earnings, and adding the regression line to the model. And what we see here is, the people with relatively low education, they earn less, obviously. You see? So less earnings belong to people with less education on average. And the second thing is that as the education level gets higher and higher, as education level gets higher and higher, you get more and more deviation in earnings. Okay, I guess here we got a little bit problem. Here, I believe the education should be in the. I believe it should be reversed. Education should be in the x-axis and earnings should be in the y-axis. So basically, as we increase, so it should be education. I'm sorry. Education earnings should be here. So as we increase the education level, mean earnings are also increasing, and also the variance of earnings are increasing, and therefore you get the deviation of these data points from the perfect line is basically increasing on average. Yes, so you can see that the average, the standard deviation of errors are increasing as you increase the education level. So that is the real life example of heteroscedasticity. Now let's have a look at this problem, how we can get around this problem. To get around this problem, we have to use this formula. The formula for the general formula for standard errors. Okay, the standard error of beta 1 hat should be equal to this guy. You see here we add variance of epsilons, which is varying by observations, by x's. As x's are changing, the variance of errors are also changing. But suppose these variances are constant. Okay, if they are constant, then you could basically simplify this formula out. You could if suppose this is equal to sigma squared u, and this is equal to some constant, obviously you can take it out of this summation, and what you're going to get is you're going to get the same things in the numerator and denominator, except the denominator has, power of 2. So you cancel these things out and you receive a simplified formula. So basically, whenever your variances are constant, then the standard errors, the standard error formula is simplified to this formula within the red rectangle. And actually, the summary function and confidence function in R, they are using this homoscedasticity only errors. Okay, homoscedasticity standard errors. They are presupposing that the variance of errors are constant. So errors are homoscedastic. Okay, homoscedastic means that errors variance do not change. Okay, but in reality, we could see that in real life examples, it may happen that the variance is varying by x values. Therefore, it is always better to use the general formula. If you have homoscedastic errors, no problem, you will get it correct. And also, if you have heteroscedasticity problem, if you have homoscedasticity, actually, homoscedasticity is not a problem. Homoscedasticity is a good case. It's simplifying our lives and simplifying the formula, as you can see. But if you always use the general formula within this red rectangle, that is better, because in both cases you are going to have correct standard errors. Okay? And now let's have a look how we can do it in R, how we can perform hypothesis testing using the heteroscedasticity consistent HC standard errors. To do that, you have to use this V called HC. You see, and then you put the linear regression model that you have already estimated, and use the V-curve variance covariance matrix with heteroscedasticity consistent errors, V-curve HC, linear model, and type is equal to HC1, heteroscedasticity consistent error, type 1. You see there are many types, but usually we use HC1. And then you take the diagonal elements of this matrix, and then you use another function called coefficient test, linear model, and you have to supply the V-curve. Okay, and in that case we receive this kind of output. And here the errors, the standard errors in this case, they are actually consistent with heteroscedasticity problem. If you remember, in the previous example we received like 73 for t-test for the intercept estimate, and for the slope we got something minus 4.5, I believe, as far as I remember. You see, now after you used those heteroscedasticity consistent errors, standard errors, they got kind of smaller. I mean, they can be larger than smaller. It depends on the case, but the most important thing is that you have to take that problem into account. You have to account for the fact that errors can be heteroscedastic. Okay, that is the formula to use it. Remember that. You have to use coefficient test function, not summary function. Okay, and you have to supply the corrected standard errors by using this V-curve. Okay, and we have some other formula, some other useful function that is called linear hypothesis, and that comes with the CAR package. card library. If you have not installed this card library, please install that. What is the essence of linear hypothesis testing? That is that the summary function and co-test functions, they are actually testing the standard default null hypothesis in this form, that true parameter value is equal to 0. But it may happen that you may be interested in testing the hypothesis in this form, that for example beta 1 is equal to 1, right, or 2, or some other value other than 0. Okay, in that case, linear hypothesis function is very useful. Actually, you can use this function to test any linear hypothesis about the model parameters. And in future, when we are going to talk about multiple linear regression models, we will see that, we can use this linear hypothesis function to test the linear combination of the parameters, not only each parameter individually. Okay, you see, again, summary function, co-test functions, they are able to test equality of true parameters to 0 only. But linear hypothesis function is helping us to test any linear hypothesis about model parameters. Okay, and how you do that? This is very simple. You have linear model, you have linear regression model, that we suppose that you have already estimated the linear model. You just supply it, and your hypothesis is that beta 1 is equal to 1, for example. So you basically say that ASTR, instead of beta 1, it's a bit strange, because instead of beta 1 you actually write a variable which is multiplied by beta 1. Okay, you say STR, the coefficient of STR is equal to 1, and then you say adjust. These standard errors, by the way, they're called White standard errors. White was the person who in 1980s who I think came up with this heteroscedasticity problem and how to get around this problem. Therefore, we say White adjust, and we choose the type HC1. If you don't supply anything, you see, linear hypothesis function will also use the homoscedasticity assumption, which is not true in real life most of the time. So what we receive, the output you receive is this. You see, it is an F-test now. F-test value is very large, it's 39. If you want to use critical value approach, you have to go to F-table, and you will have to search for, you see, enumerated degrees of freedom equal to 419, and denominated degrees of freedom is equal to 418. So you have to choose the critical value from the table. But this is a hard way of doing it. Look at the p-value. What you see is p-value is just equal to 0. It means that we know that if p-value is less than the significance level, alpha, then we have to reject the null hypothesis. You see, in this case, we got p-value very close to 0, and because of rounding, it shows up as 0, right? So we got p-value of 0, which is far less than 5%, and therefore we reject the hypothesis that beta 1 is equal to 1 in this particular case. Okay, as simple as that. I'm sorry, here we got another mistake. So because p-value is very small, even smaller than 0.1%, we reject the null hypothesis that beta 1 is equal to 1. Okay, remember that. Now let's conclude the lecture. You see, the previous assumptions, that the model is linear in parameters, the exogeneity assumption, the IID assumption, finite kurtosis assumption. If you add one more assumption, which is homoscedasticity, in that case you get the best linear unbiased estimators. So OLS estimators that we have already derived, they are going to be not only unbiased, they are going to be best linear unbiased estimators among all linear estimators. Okay, best means that the OLS estimators will have the smallest variance among all linear estimators. Linear means that your model is linear in parameters. You see, oh, I forgot xi here, another mistake. You see, yi is linear in parameters. Beta 0, you don't have beta 0 square or log of beta 0 or beta 1, okay? Parameters, so yi is linear in parameters. Meanwhile, remember that in future classes we'll see that you may have this kind of regression function, beta 0, beta 1, xi plus beta 2, xi square, and so on and so forth, right? So we are talking about linearity in parameters, not in regressors. So it may be, yi may be nonlinear in regressors, but it should be linear in parameters, okay? That is the essence of this first assumption. Okay, if these 5 assumptions hold, then OLS estimators are going to be best linear unbiased estimators. That is called Gauss-Markov theorem, okay? That is the essence. Okay, conclusions. In this lecture we discussed the following key points. We said that if you have first 3 assumptions, then you are going to get unbiased and consistent OLS estimators. Also, they are going to be asymptotically normal, so CLT applies. If you have these 3 assumptions, CLT is going to apply to OLS estimators. But these 3 assumptions are not enough for OLS estimators to be best, to be the smallest, to be of the smallest variance among all linear estimators. Okay, so we need to add homoscedasticity assumption. If you have these 3 assumptions plus homoscedasticity, then you are going to get blue estimators, best linear unbiased estimators among all linear estimators. Okay, and also we learned that homoscedasticity is kind of life simplifying assumption, but it may not hold in reality. We may face the problem called heteroscedasticity, and in that case we have to use heteroscedasticity consistent standard errors to ensure that our hypothesis testing and confidence interval estimates they are valid. Otherwise, remember, heteroscedasticity problem is affecting your inference procedures, your hypothesis testing procedure and confidence interval procedures. They are going to be wrong if you have heteroscedasticity problem, but if you ignore it, your hypothesis testing and confidence interval procedures, they're going to be totally wrong. Okay, remember that. For that, you have to use heteroscedasticity HC standard errors, and we have learned how to do it, how to perform that in R using the coef test function in conjunction with vcof function, if you remember. Also, we talked about linear hypothesis function in R, which is helping us to test any linear hypothesis related to the model parameters. Meanwhile, coef test and summary and all other functions, they are testing the equality of parameters to 0 only. That is the default hypothesis that they can test. But linear hypothesis function, it is very useful. You can both use heteroscedasticity consistent errors, standard errors, and also you can test any linear hypothesis about the model parameters. Remember that, okay? Thank you very much. Hope to see you in the next lecture.